Beyond traditional computing, embracing the neuromorphic approach. Traditional computing relies on separate processing and memory units. This architecture, known as the von Neumann architecture, faces limitations when it comes to tasks like pattern recognition and learning. These are tasks that the human brain performs effortlessly. Neuromorphic computing offers a different approach. It takes inspiration from the structure and function of the human brain. By mimicking the brain's architecture and operation, neuromorphic computing aims to overcome the limitations of traditional computing. Neuromorphic computing is particularly well suited for tasks that are challenging for traditional computers. These include tasks involving complex patterns, real-time processing, and learning from large datasets. Examples include image and speech recognition, natural language processing, and robotics. Neuromorphic computing represents a fundamental shift in how we think about computing. It moves away from the traditional sequential processing model. Instead, it embraces a more parallel and distributed approach, much like the human brain. This shift has the potential to revolutionize various fields. Mimicking the brain architecture of artificial neurons and synapses. At the heart of neuromorphic computing lie artificial neurons and synapses. These components are the building blocks of neuromorphic systems. They're designed to mimic their biological counterparts. Artificial neurons act as processing units. They receive, process, and transmit signals, much like neurons in the brain. Synapses, on the other hand, connect these artificial neurons. They play a crucial role in learning and memory by adjusting the strength of connections between neurons. The strength of these connections, known as weights, determines how signals propagate through the network. Learning occurs through the adjustment of these synaptic weights, allowing the network to adapt and improve its performance over time. This interconnected network of artificial neurons and synapses forms the basis of neuromorphic chips. These chips are designed to process information in a way that is more analogous to the brain. Unlike traditional computers that rely on separate processing and memory units, neuromorphic chips integrate these functions. This integration allows for faster processing and lower power consumption. Efficiency at its core, low power and event-driven processing. One of the key advantages of neuromorphic computing is its inherent energy efficiency. Traditional computers consume significant power even when idle. Neuromorphic systems, on the other hand, operate using an event-driven approach. This means they only consume power when processing information. When no input is present, the system remains largely inactive, resulting in significantly reduced energy consumption. This event-driven processing is directly inspired by the way neurons in the brain function. Neurons only fire when they receive a strong enough signal from their neighbors. Similarly, neuromorphic systems only activate specific parts of the network when necessary, leading to remarkable energy savings. This low power consumption makes neuromorphic computing ideal for a wide range of applications. It is particularly well suited for mobile devices, embedded systems, and applications where energy efficiency is paramount. The ability to perform complex computations with minimal power consumption opens up new possibilities for edge computing and the Internet of Things. The power of parallelism. Adaptability and scalability in neuromorphic systems. The human brain excels at parallel processing, effortlessly handling massive amounts of information simultaneously. Neuromorphic systems aim to replicate this capability by incorporating massive parallelism. Thousands or even millions of artificial neurons can operate in parallel, enabling the system to process information much faster and more efficiently than traditional computers. This parallel architecture also contributes to the adaptability of neuromorphic systems. Learning and adaptation occur through the adjustment of synaptic weights between neurons. As the system is exposed to new information, these weights are continuously updated, allowing the network to adapt to changing conditions and improve its performance over time. The scalability of neuromorphic systems is another key advantage. Researchers can increase the complexity and computational power of these systems by adding more artificial neurons and synapses. This scalability allows for the development of increasingly sophisticated neuromorphic chips, capable of tackling even more complex tasks. The unique capabilities of neuromorphic computing make it a transformative technology with the potential to revolutionize various industries. From artificial intelligence and robotics to healthcare, the Internet of Things, and autonomous systems, the applications are vast and far-reaching. In AI, neuromorphic computing can enhance pattern recognition, natural language processing, and machine learning algorithms. This can lead to more sophisticated AI assistants, improved fraud detection systems, and more accurate medical diagnoses. Robotics can benefit from neuromorphic computing's ability to process sensory information and make real-time decisions. This can lead to more autonomous and adaptable robots capable of navigating complex environments and performing intricate tasks. In healthcare, neuromorphic computing can revolutionize prosthetic limbs, brain-computer interfaces, and drug discovery. The Internet of Things can benefit from the development of energy-efficient neuromorphic sensors and devices, enabling more intelligent and responsive systems. Autonomous systems, such as self-driving cars and drones, can leverage neuromorphic computing for real-time decision-making and navigation in dynamic environments. Several research institutions and companies are at the forefront of developing neuromorphic hardware. IBM's True North chip, for example, is a notable example of a neuromorphic chip designed for low-power real-time processing. It features millions of artificial neurons and billions of synapses, demonstrating the potential for massive parallelism in neuromorphic systems. Intel's Loihi chip is another prominent example of neuromorphic hardware. Loihi is designed to support a wide range of AI applications, including robotics, autonomous vehicles, and natural language processing. Its architecture incorporates learning capabilities, allowing the chip to adapt and improve its performance over time. Spinnaker, developed at the University of Manchester, is a neuromorphic supercomputer designed to simulate large-scale brain models. It consists of millions of ARM processors interconnected to mimic the structure of the brain. Spinnaker's unique architecture allows researchers to study brain function and develop new neuromorphic algorithms. These examples highlight the progress being made in developing sophisticated neuromorphic hardware. As research continues, we can expect to see even more powerful and efficient neuromorphic chips emerge, further expanding the possibilities of this transformative technology. While neuromorphic computing holds immense promise, several challenges remain before it becomes mainstream. One of the key challenges is hardware scalability. Building larger and more complex neuromorphic systems with billions or even trillions of artificial neurons and synapses poses significant engineering hurdles. Software development for neuromorphic systems is another challenge. Traditional programming paradigms are not well suited for the parallel and event-driven nature of neuromorphic computing. New programming languages, tools, and algorithms are needed to fully harness the potential of these systems. Integrating neuromorphic systems with existing computing infrastructure presents its own set of challenges. Developing interfaces and protocols that allow neuromorphic chips to communicate seamlessly with traditional computers is crucial for widespread adoption. Perhaps the most fundamental challenge is our incomplete understanding of the human brain. While we have made significant strides in neuroscience, many mysteries remain about how the brain learns, adapts, and performs complex computations. A deeper understanding of the brain is essential for developing more sophisticated and capable neuromorphic systems. Neuromorphic computing represents a paradigm shift in computing, moving away from the limitations of traditional architectures and drawing inspiration from the incredible processing power and efficiency of the human brain. While challenges remain, the potential benefits of neuromorphic computing are vast. As research progresses and these challenges are addressed, neuromorphic computing has the potential to revolutionize various fields. From AI and robotics to healthcare, the Internet of Things, and beyond, neuromorphic computing could usher in a new era of intelligent and efficient devices and systems. The journey towards truly brain-like computing is still in its early stages, but the progress made so far is encouraging. As we continue to unlock the secrets of the brain and develop more sophisticated neuromorphic hardware and software, we can look forward to a future where computing is more powerful, efficient, and integrated into our lives than ever before.